Welcome, everybody, and thank you very much for joining us for this webcast seminar, Powering the AI Revolution, which is going to discuss in detail digital electricity's use in the data center. We at Cabling Installation and Maintenance are grateful to VoltServer, the inventor of digital electricity, for making this seminar possible through its sponsorship. We're also extremely grateful that VoltServer has offered up Rona Davis, its Chief Revenue Officer, as today's expert who will deliver the slides that you'll see today. I'm going to get out of the way very quickly to turn it over to Rona, but before I do, just want to let all you members of our audience know a couple of things. The question button that is in your window is how you can communicate with us. You can communicate with Rona that way. We're going to have a Q&A session to end this seminar, so please send any questions you have at any time using that question window. We will see them here, and we'll have a Q&A, as I mentioned, with Rona to wrap up. That question window is also where you can ask us for any type of tech support if that's something you need. If something doesn't look right or sound right with how this webinar is being presented to you, please use that question window. We've got some help here, and we'll try to help you troubleshoot whatever's going on behind the scenes. Also, there's a resources tab at which you can find some information related to today's presentation that VoltServer is making available. Please make your way there if you wish. That resources tab is where you can find some helpful complementary information to what Rona is going to present here today. Finally, back on the topic of this presentation and how it looks and sounds to you, it's best if you're able to close other applications on your device for optimum performance of this webinar on this platform and how it is presented to you. So if you're able to close those other applications and just have this open, we appreciate that attention, and we think that'll offer up the best results. So again, please send those questions Rona's way anytime. We'll have a Q&A to wrap up, and now it is really time for me to get out of the way and turn it over to today's expert speaker, Rona Davis with VoltServer. Rona, whenever you're ready.
All right, thank you, Patrick. And we're excited to be on the CI&M platform today, talking with your customers about powering the AI revolution, the application of digital electricity in the data center. And it's actually one of my most favorite topics to talk about. It's so exciting, especially for the structured cabling industry. It presents a great opportunity. I'm going to move through the slides pretty quickly today. And it's a new topic, so don't expect to be an expert by the end of this call, but we will provide these slides as a handout, and if you would like a more detailed presentation or like a deep dive session with your team to review the technology and see how it would fit in your application, please reach out to us. We're happy to do that. So with that, I'm going to go ahead and get started here. Well, AI in the data center is presenting some unique challenges for our customers, and we're really needing to rethink power distribution from the grid to the server. Now, today we're going to talk about the power distribution from the gray space through the white space and to the server cabinet. We are confident that digital electricity can help solve some problems for our customers. AI uses extremely high power loads to support very dense clusters of GPUs that are orchestrating simultaneously and that also have a unique power profile compared to traditional data center loads. We also have to consider that data centers will still have all of the typical data center areas and loads that we have today. So we're going to be operating in this environment where it's sort of a hybrid, where you've got all of the traditional data center stuff, but then you have these AI factories inside of data centers as well. And we're up against a significant electrician shortage. That's expected to span several years. And AI is a race, right? Deployment speed is important for us to consider, as many of the data center projects have very aggressive build schedules. And there is plans to increase the voltage level in the data center. That's something that's being discussed right now using traditional power technology. Now, while this will support higher power densities, those higher voltage levels that are being considered will bring safety challenges that may not be practical for all data centers, especially those that have a high move, add, and change environment. So VoltServer, as Patrick noted, is the inventors of fault managed power. We call our fault managed power digital electricity. So you may hear me use those terms interchangeably today. This is how it works. We take power from the utility or your UPS, BESS, or on-site energy source, and we convert that power into a digital packet format. Our patented process is called packet energy transfer. Those packets of energy flow across structured cabling to a receiver that accepts the digital electricity and converts it back into a traditional analog power type to power a local load. Now, each one of our energy packets includes a data for a safety check on the line. We are constantly monitoring the line for any fault or decay. And if a fault is detected, we don't send that next packet of energy. And this happens very quickly, under 4 milliseconds. And it limits the amount of energy into the fault to such a level that it will not cause electrocution or fire. This is what makes our technology safe to interact with and eliminates the need for breakers, arc flash protections, conduits, and lockout tagout areas. Our transmitter is, in effect, a solid state transformer. Now, the technology has been codified under Article 726 of the National Electrical Code. And under that article, it limits fault managed power to a maximum of 450 volts. VoltServer's solution operates at 350 volts DC. There is also a corresponding UL safety standard that is UL 1400. And UL 1400-1 is for the active equipment and for the system. And UL 1400-2 is for the cabling for the system. Now, I want to show you guys just a comparison of a traditional electrical distribution to a fault managed power distribution. Just kind of how the lineups are, how the different components compare in a lineup. So first, with your electrical sub panel, that would equal a power transmitter in an FMP lineup. Your breaker, that actually is just a channel on our transmitter. And then your conduit and your wire, so that pipe and wire, that actually becomes UTP cabling or a structured cabling system. And then the receptacle, that actually equals our receiver, or today we're talking about the data center, so it's our receiver server PDU. Now, because digital electricity is a digital technology, data is intrinsic to the system, so there isn't any need to add additional systems for monitoring and control onto those onto an analog electrical system. And if you've ever done that, if you've ever added controls onto a traditional energy system, you know that it's quite costly, especially to get individual circuit level monitoring and control. Now, our API provides a very simple integration into other higher level systems like your EMS, BMS, and DSIM. The management platform allows you to set policies and priorities for every single circuit in your facility. Now, in AI data centers, not all the real estate is equal. Actually, the physical space closest to the AI GPUs, which demands lots of power and cooling, becomes especially valuable. And that is because that space enables the infrastructure required to support AI, those processors. Now, this graph represents the value of data center real estate from the gray space to the AI server cabinet. To support AI performance, it's critical for us to shrink the footprint of power distribution as we get closer to those AI servers. This frees up valuable space and enables AI data centers to operate at peak compute efficiency. So let's take a look at a standard AC 2N data center lineup. So this probably looks pretty familiar to you if you work in data centers today. Maybe your lineup varies slightly, but the gray space, typically you would have your main power entrance facility, your UPS, your main switchboard. Sometimes there is also a static transfer switch in there. Then in the white space, you would typically have your floor distribution to the floor PDUs. And then from the floor PDUs, you have busways, busway taps, and vertical server cabinet PDUs. Now you have this lineup both for the A and the B sides of a 2N architecture. Now we're going to take a look at a digital electricity lineup in the data center. Now in your gray space, you have your power entrance facility that feeds your UPS transmitter rack. In this case, we are showing 160 kilowatt UPS and 160 kilowatt transmitters, which for comparison, our transmitter would be like the floor PDU in a legacy AC system. Now, from your 160 kilowatt UPS transmitter rack, we have 8-pair 12 to 16 gauge UTP cables in an open basket tray. So it's actually a pretty small cable bundle for that power level. That bundle runs in the basket tray to the server cabinets in the white space where the UTP cables terminate to our high voltage DC PDU. The 350 volt high voltage DC PDU has 4 power sleds. Each can accommodate their own diverse power source. Now, for this example, I'm showing a 2N architecture, but our technology can use the optimal N+1 architecture for resiliency. Now, as you can see, digital electricity eliminates a lot of stuff in the data center, and the architecture is considerably simplified. Now, I just wanted to show you guys a closer look at the transmitter and the wiring. So this transmitter, it's going to sit in the gray space, right, in that transmitter UPS rack. I'm showing our 40 kilowatt transmitter. It has 16 3-kilowatt channels, and we're using 2 8-pair cables for each of those 40 kilowatt transmitters. So remember that 350 volt high voltage DC server PDU has 4 power sleds, right? Well, this diagram demonstrates how you can achieve an N+1 architecture sourcing from 4 unique transmitters that could have 4 unique power sources for a 100 kilowatt N+1 in only 2 rack units at the server cabinet. So I'm going to say that again because this is really a key differentiator here with fault managed power in power density to the rack. This is a 350 volt high voltage DC server PDU. It has 4 power sleds. Each of them can have their own, can be fed by a unique transmitter. Each transmitter can have a unique power source to accomplish 100 kilowatts N+1 in only 2 rack units at the server cabinet. So each of those PDUs total will be 67 kilowatts and a 50 kilowatt. For N+1, that equals the 50 kilowatts. Okay, now we're going to get inside of that 100 kilowatt N+1 server cabinet and look at how the power is distributed to the AI servers. We have 2 PDUs, each with 4 power sleds, and each power sled has 2 high voltage DC power outputs. Each of those outputs supports 2 AI server power supplies with a Y-style power cable. You'll have plenty of space for those power cords, and importantly, you're going to have room to distribute the liquid cooling that you're going to need for your GPUs when we're operating at these power levels. Okay, pan back, and we'll take a look at the gray space in a 4 megawatt, 3 megawatt N+1 edge or enterprise data center. Now with digital electricity, we will accomplish this with 25 160 kilowatt UPS transmitter cabinets. Very, very modular. This requires a square footage footprint of 234 square feet for both the UPS and the transmitter. Now remember that the transmitter is equivalent to a floor PDU in a traditional AC power lineup. In comparison, a 4 megawatt UPS in a traditional data center would require a minimum of 236 square feet, and 4 megawatts of floor PDU will require an additional 84 square feet for a total of 320 square feet. That is a pretty significant square foot savings, especially when we're operating at scale. Now, traditional thinking would actually lead us to believe that going with bigger UPSs and distribution equipment instead of a modular approach would save us space, but that's actually not the case. Using smaller modular components in a DE system uses less space, and there is currently, and at least for the foreseeable future, far less supply chain constraints on smaller electrical components than the big electrical components. So now I want to head over into the white space, because that, of course, is where the real AI magic is happening. Okay, you probably notice immediately the absence of multiple levels of bulky busway and floor PDUs, right? In fact, the slide was so empty, I had to fill it up with this little star of the up to 84% saved in power distribution. Now, when we look at coming from the gray space, you have that open basket tray with the UTP cables feeding each server cabinet that is powered at 100 kilowatts N plus 1. All that space that you have recaptured from not using the busways or having floor PDUs or having sidecars can be used to load up more GPUs in your clusters, both up and down and side to side. Additionally, you're going to have space to run your liquid cooling lines. We have a whole other utility that has to be distributed now inside of the data center. If you're looking at brownfield spaces, where is it going to go? Well, if we can reduce the required space for power, we can recapture that and we can use it for some of our cooling line distribution. Now, in the compute area, digital electricity can save up to 84% of the space over the AC systems operating at these power levels. Okay, so we've talked about the three components of the system. That's our building blocks. The power transmitters, your cables, and the receiver slash server PDU options. And we are advancing our roadmap at VoltServer at a breakneck pace and expect to be able to support data center demand beginning in 2026. And so I want to kind of go through the three phases of product roadmap, and because it does address density and additional applications as well. So when we look at what's available now or within the next 9 months, we have today our Tetra, our 6 kilowatt transmitter. It has 1500 watts per channel, and it can take inputs of 208 to 277 volt power input. So you can use it with a 3-phase power using that 277 leg. And then for cables and connectivity, today there are cables out on the market, 12 to 16 gauge class 4 cables, 4 pair to 8 pair, suitable for the data center environment. But those are just bulk cable options. And then for the server PDU, a 24 kilowatt server PDU, that's 350 volts high voltage DC output. It's 6 kilowatts per power sled with 4 sleds, and that's going to be 18 inches deep. And then the next phase for us is on the transmitter. It's our Tetra AC that is 36 kilowatts and 5 rack units. And this is where there's a significant jump. We're going from 1500 watts per channel to 3000 watts per channel. And this again can accept 208 to 277 or a high voltage DC power input. Now, let's talk about the cables now and where we're moving towards in cables. So looking at 12 to 16 gauge class 4 cables, pre-terminated cable assemblies that have terminal blocks on the ends of them. This is going to help for a faster installation out in the field. And then going down into our PDU options, we are also adding a 2-rack unit 7.6 kilowatt AC server PDU, and it will have 4 208 volt AC outputs. We do think that going high voltage DC in the data center certainly is going to help with efficiencies. It's simplified, and that is the lowest cost option for power distribution in the data center. But we expect that customers are still going to have some loads that they can't get a high voltage DC power supply for. Maybe a specific application server from a vendor, right, that you need to support. So we want to be able to, for those lower power loads, support those with an AC option. So what's really cool about fault managed power is that doing that power adaptation at the end allows for flexibility at the server cabinet level, so that you could use a high voltage DC, which is the most efficient, lowest cost format, or you could use a low voltage DC distribution at the server cabinet, or you could use an AC distribution at the server cabinet as well. So then when we look into really kind of moving into late 2026 and into 2027, on our transmitters, we're going to have a 3-phase direct input transmitter. Again, that's 3 kilowatts max channel output. Both the Tetra AC and the Tetra Max will have 16 channels. But the Tetra Max will be 40 kilowatts plus and 4 rack units, so a little bit better power density than the Tetra AC. Now, this is when things, in late 2027, this is when things get really exciting around the cable and connectivity. There is a connector that's under development for fault managed power, and that is going to really be able to provide this plug and play solutions for power in the data center. And I think it's a really, really exciting opportunity for the structured cabling industry. So you're looking at 12 to 16 gauge UTP cable that are pre-configured and pre-terminated cable assemblies, those cross-connect fields and connectorization options, both field terminated and factory terminated options. Now, when you get into the server PDU options, this is when we will have the 67 kilowatt server PDU that gives you that 50 kilowatts N+1 in a single rack unit, 350 volts high voltage DC outputs. And remember, it's going to have those 4 power sleds, each one of them being 16.7 kilowatts. And and then from when everything's going to be available, the PDU will be late 2026. The Tetra Max is 2027, and the connectorized solutions are 2027 as well. Anywhere where we have orderable now on there is really kind of just to let people know that we are building capacity within our supply chain. So many of these products are orderable now, and we certainly are looking at wanting to get a good understanding for capacity planning for the next few years. So VoltServer is a fault managed power technology company, right? That is that's all we do all day, every day is digital electricity. And so we have formed really strong partnerships with some leading organizations that package our technology. They provide complete end-to-end solutions, as well as service and support models. And so when you think of VoltServer as a core powering technology that likely is going to reside in many different systems as the core power technology. But those systems need to be wrapped around with all of the components so there can be a full end-to-end solution, and also be able to have the service and support model, the certified installers and distributors, and to be able to scale globally for our customers. We're very, very proud of the strategic partnerships that we have formed so far. This also gives you a good idea of the level of investment around this technology within the industry. This is VoltServer's strategic partners, but there are many more within that are part of the Fault Managed Power ecosystem. In fact, if you're interested in learning more about Fault Managed Power being part of this movement to save sustainable power, you can go to the fmpalliance.org, fmpalliance.org, and you can join as a member of the FMP Alliance. We're actually starting a user group, which I think will be a great opportunity for new adopters and some of the older adopters that have been using Fault Managed Power for a while to actually collaborate with other users on application uses, etc., through the FMP Alliance. And VoltServer is proud to be a founding member of the FMP Alliance. I am the secretary of that alliance. So why should you use digital electricity for your next data center? Well, like all things in life, it's math. Digital electricity is the digital transformation of legacy power systems. The digital technology enables the discrete data and management of every single circuit in your facility. Digital electricity's modularity allows stakeholders to pay as they grow, and the technology scales to support the smallest edge data center all the way to a hyperscale. It has a reduced footprint that is so critical, especially at the server GPU for that peak compute output. Our unparalleled safety means that power can exist in places that it can't with traditional power systems, and it's going to allow for a workforce that can be skilled up quickly to close that significant electrician gap we're facing for years to come. Now, all of these things add up to real economic value for the entire data center ecosystem. The developers, the installers, the operators, the customers, and the community constituents. So with that, I think that I'm going to turn it back over to Patrick, and he's going to prepare for the Q&A section.
Rona, thanks very much. Thank you for all that information, enlightening and thought-provoking, as our question queue indicates. Thank you to those of you who submitted questions. We're just going to gear up for that Q&A segment in a moment. In the meantime, though, while I have your attention, I want to remind you that the slides that Rona presented here today are available for download and for your use in the Resources tab, at the Resources tab that you see on your interface, along with a PDF copy of this presentation are a couple of other assets from VoltServer, getting into detail about some of what Rona presented here today. Some detailed information. There's a white paper. There's not exactly a spec sheet, but it's another document that talks about the value of digital electricity in the data center. So just want to let you know or remind you that those resources are there, available from VoltServer here on this platform for your use. Also, appreciate everybody who joined us here today, and want to let you know that this seminar is going to be available for viewing on demand. We're now live on the 19th of November. Just about 24 hours from now, the 20th of November, this will be available for on-demand viewing. So if you wish to come back and take another look and listen, you will be able and welcome to do so. We also welcome and appreciate your consideration in sending a link to this presentation to some of your colleagues, some of your co-workers, some of your friends in the industry who you think may benefit from finding out more about the use of digital electricity in the data center. So this will be available for on-demand viewing for a period of 6 months starting tomorrow. We welcome you coming back and taking a look, and also welcome and appreciate you passing along the word that this seminar is available if you indeed found it helpful. I now have the courage to look over at the question queue and see where it stands, and it is it's quite populated. Rhoda, I hope I've given you enough of an opportunity to have a sip of water and clear your throat and get ready for a lively Q&A session. Do we have you still?
Yeah, and it looks like we've got some good questions in the queue, Patrick.
We do. Thank you. I'm just going to get started right away. So thanks again, Rona, for the information you presented. I'm going to get right into the questions. One asks, will the technology that you're talking about, digital electricity, work with open compute? That which is quite a topic of discussion and interest in the data center. So does it work with open compute?
Yeah, so I guess the short answer is yes, but I'm going to explain how. So we know that open compute at the rack basically is that rack rail, or the power rail for open compute is at that 50 volt range. And so fault managed power, you can take fault managed power to the cabinet. Our output is high voltage DC. And many of the open compute power supplies that are on the market actually can accept that high voltage DC input that then, of course, down converts to that 50 volt to power the rail. Now, our current format doesn't have the right types of connections to wire into the open compute power supply. That is something that we have considered adding to our roadmap. So if there is anyone looking into open compute, please reach out to us, because we haven't had specific requests for it. We have evaluated it. We certainly can work within that environment, but we don't have a product specifically with those connections to connect into the open compute power supply today. But the technology can absolutely do it and support open compute.
Thank you, Rhoda. Next question is about efficiency. What kind of efficiency does fault managed power have or offer?
Yeah, so fault managed power is a DC power technology, and we know that most of the equipment that we're going to be interfacing within the data center is natively DC as well. Our power efficiency is very comparable, in fact, slightly more efficient than a traditional AC lineup in a data center. And but it very much depends on what your lineup looks like. But we have done several models where we are comparable or slightly better than an AC power distribution.
Thank you, Rona. The next one asks, are electrical contractors, limited energy systems integrators able to partner with VoltServer? And if so, how are these professionals able to partner with VoltServer in marketing and installing that class 4 fault managed power system? We're talking about existing opportunity, existing locations, new opportunities. Just, I guess, looking for a how-to in terms of integrators partnering with VoltServer.
Yeah, absolutely. So VoltServer certainly works directly with contractors and integrators, but we also have our solution partners that you can work with as well. So there's multiple paths to partner with VoltServer or our ecosystem of solution partners.
Thanks, Rona. Safety, the safety question. Is this type of digital electricity safe to use for my commercial access points?
Yes, absolutely. It is safe. The safety of the circuit or the safe portion of the circuit exists between the transmitter and your receiver. That is completely safe. So it doesn't really matter what that application is or that use is. That circuit is always safe between the transmitter and the receiver.
Thank you. Next question has a bit of detail to it, talking about anytime the letters AHJ appear in a question, it never seems to be a simple one, and that's the case here. I'll just read the question essentially verbatim. Do you have an example drawing, a sample drawing from an electrical engineer that shows how these systems are documented on permit drawings. Um, this attendee is looking for possible details, work notes, and looking for information on how AHJ's, authorities having jurisdiction, are typically seeing these on drawings that are signed by an electrical engineer for approval. So, like I said, not a simple question, but AHJ approval, I guess, is not a simple process. So that's the one we're asking you at this point.
Yeah, actually, it's a great question because this is relatively new. So we do have solution partners that are creating all of those CAD files that can be included into your drawings, and then we do have some work on the Division 27 specification that has hooks into Division 26 as well, to be able to include in specification document. I will say that those things are early, and we're building more and more tools. A lot of our solution partners will likely be the ones that support us to deliver those that's basically the documentation and tools that will help you to specify and to design and specify utilizing digital electricity. And so on that question specifically, I would ask that you reach out to me. And if we don't have the tools that you're looking for, one of our solution partners likely does, and I can connect you with them.
Thanks, Rona. I'm going to jump to sort of a follow-up or a tag-along question that was submitted by the same attendee. So thanks very much for your attendance here today, your interest in the questions. We're getting to both of them. The follow-up is there a master spec specification that engineers can use to convey the performance and installation requirements for digital electricity systems?
Yeah, we do have a Division 27 that has some hooks into Division 26 that we are happy to share with you. Probably will require some modification for your unique project. I think that's pretty standard. But yeah, we do have the base document for Div 27 in the master, in the CSI master format. It has some hooks into 26 as well.
Thank you. The next one is a short question that maybe could be longer and maybe elicits a long answer. Price differences. Are there price differences, cost differences, maybe TCO, whatever direction that goes in, for digital electricity versus your traditional powering systems?
I love that somebody asked this question. Most people don't like to deal with price, but I actually love to have this conversation because so you could look at it, and I would say pricing is comparable to existing power systems today, but there is an opportunity for cost savings. There is a significant reduction in labor to deploy these systems, and so depending on what your architecture is and kind of what your deployment model is, what region you're working in is going to impact your labor rates. But in general, we price out the same or better. Okay, so we'll level set there. But where we can bring a lot of value to data center customers, the people who are building them or operating them, is both from how quickly you can design our systems, right? So you're gonna design these systems. It's gonna just take less time to design them, but also is the deployment speed. The fact that we can get out there and get these data centers up and running faster. And I think especially with these constraints that we're seeing both from supply chain on equipment to the shortage of skilled labor, that this is a place where we can help. Time is money, right? Or what do they say? Speed is currency. And so there's that. There's also that you can deploy our systems in a very modular way. If you remember, I was showing 160 kilowatts at a time that can be deployed in the gray space. So imagine where you set up your gray space, you've got your main switch panels in there, you've got your busway, you build out your busway in the gray space from your main switch panels. Then as you grow, you add these 160 kilowatt transmitter UPS cabinets that, by the way, can be completely prefabricated off-site. Right. And so you literally, you can have a plug and play type of solution, 160 kilowatts at a time. What does that mean for someone who's building a data center or for a data center operator? Well, it means that as they either grow in tenants, they grow in, if they're building out their own infrastructure, that they can pay as they grow. They can hold on to some of that capital expense for a longer amount of time. And that's going to allow them potentially to do a lot of things, maybe start another data center site, right? And so the fact that our system is modular and scalable means that that data centers really can pay as they grow. And then let's not forget, speed is currency. So if they're able to deploy faster, or if we're able to allow them to recapture space that previously was used for electrical, and now that they can use it to get liquid cooling into a data center, and now don't have to go rebuild or do a very, very deep renovation on a data center, that is going to save a significant amount of time and money for our customers. Hopefully that answers the question.
I think so thoroughly, and I also think it's a good time for me to remind everybody who's online today that this is going to be available for on-demand viewing. So if you're not old like me and studied shorthand at any point in your life, and you didn't get everything that Rona just said, come on back. I appreciate that answer, Rona. It's very descriptive and comprehensive, and it is probably worth another listen. So it just gives me an opportunity to remind everybody this session is going to be here, available for on-demand viewing and listening. And please do that, because there's something to learn every minute. Moving on, you mentioned both cooling and gray space in your last response, and they both factor into this next question. How much cooling do the transmitters require in the gray space?
Yeah, so that is a highly technical question. So I'll want to probably get back with the specific answer to you on BTUs of heat that are generated in the gray space. I will say our transmitters are built to actually exist in the environmental conditions of a gray space. They do not require the level of cooling that you would have in the white space. And so that equipment absolutely can operate within the gray space. And we don't expect any requirement for any significant add of cooling or conditioning to that space. But that's when I want to get you the very specific details on the BTUs per transmitter.
Thank you. Next question asks, digital electricity's modularity. If you compare and contrast digital electricity modularity versus traditional large PDUs, does digital electricity increase reliability? Does it also affect in any way any emergency repair operations?
Yeah. Okay. So when we look at going to a modular system that uses smaller components versus the larger UPSs and floor PDUs, breaking it down into smaller chunks is going to improve reliability. And it does improve repairability, and I think probably most important, mean time to repair. So very quickly, you could see in the way that you could look at it in 40 kilowatt chunks, right? So you've got a 40 kilowatt transmitter that may have a repair. Let's say that you had a repair for a power supply. The power supplies are hot swappable, right? So that can be repaired in minutes. When you look at even pairing it with that smaller UPS, you have lots of options to be able to repair that UPS, either switch out and or repair that UPS within a couple of hours. And if you're working with an N+1 architecture, you know that if one of your feeds is coming from that UPS, you're not going to affect your loads when that UPS has to be repaired. So we do expect that you're going to have a quicker mean time to repair, mean time to recovery. And then when you look at the modularity of the system, it is a much smaller if you have a failure, it's going to have a much smaller impact on your data center than if, let's say, you had a UPS that was a 2 megawatt or a 4 megawatt UPS that has to be worked on and needs to be brought offline for repair.
Thank you, Rona. Next question asks about lead times, something that I think in reference to some of what you presented later in your presentation about availability. What are the anticipated lead times, on a complete system for a data center? And it gives the example of, say 10 systems, the 400/300 systems. What do you expect for a lead time for such a request?
Yeah, so once we're shipping product under general availability, we expect our lead times to be between 10 and 12 weeks. And we actually are working with some of our solution partners on getting inventory into the solution partners, actually, so that they have some product to start flowing for these data center projects. But we expect in between 10 to 12 weeks will be kind of a standard lead time for a large project. Obviously, we're working to building our capacity. The good thing about the types of components that we're using, not only is it that we're using modular, smaller electronic components that are very available within the supply chain, but also the contract manufacturing that we use has a very deep and broad footprint globally. So we expect that these products are not going to have the same kind of lead times that maybe some other larger electrical components would have.
Thank you. I'm going to maybe sneakily, in slightly different words, ask another question about costs. So it
Okay.
starts off about space. The attendee says, "I see that your calculations that you presented show a physical space saving of 84%. The question is it also true that by implementing a Class 4 fault managed power system, the result will be a cost savings of up to 40% when compared to traditional electrical distribution of feeder and branch wiring methods?"
Yeah, so we do have models that show cost savings up that high. And so that's why I always say, the caveat is kind of, what are you doing? What's your architecture? What are your power levels? But we do have cost models that show pretty significant savings when using fault managed power versus traditional architecture. One of the things, if you think about a traditional 2N architecture, you have to build out a whole A and a whole B, right? And that's busway everything. PD is everything. So you basically are completely duplicating an infrastructure. Because of all the ways that you can build diversity in with fault managed power, it really means that you don't have to build as much to actually have equal or a more resilient system. And so I think that, I guess, kind of to answer the question on price, depends on the architecture. But yes, we have seen those kinds of costs that level of savings, that in that 40% range on certain architectures within the data center.
Thank you, Rona. Next question. I presume that the receiver powers up from received power packets, but can you explain how that works? What do the transmitters consume, transmitters and receivers consume to process basically what they need to do?
Well, okay. I think that I might know where they were going with this question. So our transmitter basically is taking traditional power and it is packetizing. It's breaking it down into a discrete amount of electrons, and they're pairing that with a data packet. And that it is the point they made there is correct. It is a connected system. So if you tried to plug in a digital electricity circuit into something that wasn't a receiver, it wouldn't recognize it at all. So it does have to recognize it, and that's when it starts transmitting power. So it is a connected system. And each one of those packets that are going across that structured cabling, not unlike like our data systems, is communicating with that receiver. And if any sort of fault is detected on that line, any sort of interruption, well, that tells the transmitter not to send that next packet. So once that packet of energy reaches the receiver, then at that receiver, it then basically undigitizes, kind of like a codec, right? That is going to convert that back into an analog power signal. In this case, we're talking about just converting it into a straight 350 volt DC. There's special sauce, yeah. And I guess, Patrick, there's some special sauce in there. I'm not sure how much my engineers will let me tell you, but if you have more questions on that, we're happy to give us a call.
Thank you. Thanks very much. I've got one more question to ask you before we regroup and probably sign off. It's about keeping pace. Can the Volt server equipment that you've described here today, can that equipment keep pace with the power requirements that are growing in the data center? The growth of power requirements in the data center. Realistically, can Volt server keep up?
Yeah, so I think I talked about, so I'm going to kind of look at this from two perspectives. There's one, can the technology keep pace? Absolutely. So when we talk about 3 kilowatts per channel on our transmitter, that's pretty significant power when we're talking about using 12 gauge to 16 gauge wire in the data center. There's also there's a question of, so Volt server, can we support the growth, like how just the vast quantity, right, that's going to happen in the data center space? And I'll kind of go back to my comment about the supply chain availability of these smaller electronic components and our contract manufacturing supply chain being very broad and deep, able to produce a significant amount of equipment. So, but we're also partnered with those solution partners that are going to wrap the technology and provide end-to-end solutions. So we're not going to do it alone. We're doing it with our solution partners. We're doing it with our deep and broad supply chain. And then from again, back to the technology, when we look at looking at going to a server PDU, to that high voltage DC PDU, scaling to 200 kilowatts per rack with those high voltage DC server PDUs, we think is absolutely reasonable. And that is a good fit, up to 200 kilowatts in that format. But then there's this going to the next step, which is when we take that fault managed power, that digital electricity, directly into the AI server power supply, or right directly to an AI server with onboard power electronics. When that happens, we can get up over 400 kilowatts per rack at the current voltage levels. So we can actually deliver a significant amount of power, and frankly, more effectively than the current powering technologies that are on the market when we look at when you're approaching 100 kilowatts up to over 400 kilowatts per rack.
Excellent, Rona. Thank you very much. Thank you for that lively and an informative question and answer session, which followed a very informative presentation from you. So I thank you very much. Before we sign off, just want to remind everybody in our audience what I've told you a couple of times, but can't resist telling you again. Information about today's session is available in the resources tab, including the slides that Rona presented today, as well as some information that complements what was presented here today, meant to get you and keep you informed about digital electricity and some of its capabilities, specifically in the data center. Also, thank you for joining us live here on November 19th. This presentation is going to be available for viewing on demand beginning just about 24 hours from now on the 20th of November. I have a feeling that there's plenty of information delivered today that you'd like to see and hear again. So please know that that will be available to you. And we also encourage and appreciate any spreading of the word that you can do to colleagues in the industry or within your own organization about what was presented here today. So on behalf of Cabling Installation and Maintenance, my thanks go to VoltServer and to Rona Davis for this information. Our thanks as always. Also go to you, members of our audience who joined us. We really appreciate you being here and spending some time. We hope you'll join us again sometime soon for some more learning. And for now, we wish you all a great rest of your day. Thank you.